Hi, welcome to the IM Learning Chemistry lecture series on atomic and molecular structure. Today, I am going to discuss about energy quantization of the electrons. That means how the electrons, electronic energy are quantized, or we can say that what is the meaning of energy quantization. So, what we are going to explain today? We will explain at first what is the particle in a box concept or what is particle in a 1D box model. Then we will try to solve the Schrodinger wave equations, and from the Schrodinger wave equation solutions we will explain the concept of energy quantization. Now, why it is important? Why energy quantization is so important? The energy quantization is important because most of the we can say that all the semiconductor devices or the whole electronic industry actually depends upon the energy gap of electrons, the band gap that you already know. So everything has been designed for the concept of this energy quantization or quantum theory concept. Without this knowledge of quantum theory or the knowledge of energy quantization, we will not be able to manipulate this. We will not be able to actually design new electronics devices. So that is very important, that you must all know what is the actual meaning of energy quantization. We are able to manipulate the electrical properties of silicon or other semiconductor because we can study the wave nature of electrons, and we can, if we wanted to understand the wave nature of electrons properly, then you must know the particle in 1D box model, which is nothing but a very simplified approach to solve the Schrodinger wave equation, which is again the fundamental for all the quantum theory. So we will try to understand what is the particle in 1D box model, but before that, why it is required? It is required because it is a very common applications in a quantum mechanical model. It is very simplified system consisting of particle which is moving horizontally with an box where the it has length, a particular length, but its two side has infinite potential. That means we can say it is infinitely deep well from which it cannot escape. That means the particle cannot escape. And the solution to the problem, it gives possible values of wave function as well as the energy. And this energy actually represent only the allowed values of energy, and psi is nothing but it's a wave function. Both are very important. For this reason we need it, because when the wave function is squared, it will give the probability of locating the particle at a particular position within the box at a given energy level. That's why it's very important. Now, to solve the problem of particle in 1D box, we must follow some steps. What are the steps? These steps you need to remember. The first step is you need to define the potential energy of the particle. Then you need to solve the Schrodinger equation. The first step will be the define the potential energy. Then you need to solve the Schrodinger equation, and then you need to define the wave function. And then automatically, as soon as you solve it, you will get the allowed energies. Now, what is particle in 1D box model? Let us consider there is a box. It has a length. A. Width of the box is A, and it has impenetrable wall of the box. That means the particle cannot escape, or particle cannot penetrate this wall, because the potential energy at these two end, this side and this side, is infinity. And let's say there is a particle which is present inside the box, and particle can only move from x equals to 0 to x equals to a. The particle cannot go outside the box. And let's say the potential energy in this side and this side is, or you can say outside the box, is infinity. But the potential energy inside the box is assumed as 0. Please remember, the potential energy is taken as 0 inside the box. Now already whatever I explained, it is written here. That let us consider a particle. It is restricted to move only along the x axis and it is confined between x equals to 0 and x equals to a, because the walls are highly rigid. And let's say particle, it does not lose any energy. This is an assumption. So its total energy is constant, and it actually we can say that this box is nothing but a width of a with potential walls where the potential energy is infinity, and we can assume that particle will not be able to go outside the box. For the sake of convenience, means for making the calculation easier, we assume that potential energy equals to 0 inside the box. So now how to solve it? Because the main purpose of this particle in 1D box model is that to solve the Schrodinger wave equation. So we already know the Schrodinger wave equation for one dimension, which is d2 psi dx2 plus 8 pi square m by h square into e minus v psi equals to 0. Now we are trying to first show that outside the box particle cannot stay. So how to show that? We know that outside the box potential energy is infinity. So if the potential energy is infinity, then we can simply write d2 psi dx2 plus 8 pi square m by h square into e minus infinity, because v is infinity, into psi equals to 0. Now with respect to infinity, e is nothing, we can neglect e. So if we neglect e, then it will nothing but d2 psi dx2 minus infinity psi equals to 0, because 8 pi square m by h square, everything will be very less compared to infinity. So we can neglect all them. So d2 psi dx2 minus infinity psi equals to 0, or we can write d2 psi dx2 equals to infinity psi, or psi equals to 1 by infinity d2 psi dx2, and 1 by infinity, you all know that that is 0. So psi equals to 0. Now what is the meaning of this psi equals to 0? It means that outside the box psi equals to 0. So this is psi, not only this is psi. Hence particle cannot go outside the box. So particle can always remain only inside the box, and Schrodinger wave equations, whatever we got, we need to solve from that. So how to solve it? So if the particle cannot go outside the box, particle remain inside the box, then v equals to 0, because we have assumed that potential energy is 0. So the Schrodinger wave equation becomes d2 psi dx2 plus 8 pi square m by h square e psi equals to 0. Now this is we can say that a postulates of quantum mechanics, which we have not discussed because of the not scope of the syllabus, that for a given state of system energy is constant. So what we can write, that 8 pi square m by h square into e equals to constant, because this energy is constant. So we can write this is constant. At constant we can write anything, so I am just writing constant as k square. So what we can write, d2 psi dx2 plus k square psi equals to 0, because k square is nothing but the whole term, 8 pi square m by h square into e. So now this is very familiar. This is very we can say that familiar equation, which is nothing but a differential equation, and it has a solution psi equals to a sin kx plus b cos kx, where a and b are the constant. So for this equation, the solution is psi equals to a sin kx plus b cos kx, where a and b are the constant. Now psi can have many values depending upon the value of a, b and k, but only those values which satisfy the boundary condition, they are acceptable. So what are the acceptable solutions? What are the acceptable values for psi in this case? The acceptable values are psi equals to 0 at x equals to 0 and psi equals to 0 at x equals to a. These are the two acceptable values for psi. So now we will try to put these two acceptable conditions to solve the equation. So if we put psi equals to 0 at x equals to 0 in this equation, psi equals to a sin kx plus b cos kx, that what will happen? If we put psi equals to 0 at x equals to 0, that means a sin 0 plus b cos k into 0 equals to 0. Sin 0 0 we already know, and cos 0 1. So b into cos k0 means b into cos 0 means 1. So b equals to 0. And if we put b equals to 0 into this equation, psi equals to a sin kx plus b cos kx, then we get a sin kx plus 0 into cos kx, that is 0. So psi equals to a sin kx. So now we already get first condition, we get psi equals to a sin kx. Now if we put the second condition, that means if we put psi equals to 0 at x equals to a, then what will happen? 0 equals to a sin ka, psi equals to 0, we are putting psi equals to 0 and x equals to a. So a sin k equals to 0 or sin k equals to 0. Sin k equals to 0 means k equals to n pi. K equals to n pi because in multiple of pi, sin k will be 0, or we can write k equals to n pi by a. So now we already know 8 pi square m by h square into e equals to constant equals to k square. Now let me show from where we get this. We have already get this from here, right? I have already told that we are taking it as a constant. 8 pi square m by h square into e equals to constant, which is nothing but k square. So now we have solved it and we now get this one, k equals to n pi by a. So we will simply put, instead of k square we will put n pi by a. So n pi by a square equals to 8 pi square by m, 8 pi square m by h square into e, or 8 pi square m by h square into e equals to n square pi square by a square. If we just rearrange it, we will get the value for e. So if we rearrange it, we will get e equals to n square h square by 8m square. This is the most important equations in quantum mechanics, and this is what actually need to explain the energy quantization. Now a equals to length of the box, m equals to mass of the particle, h is Planck's constant, n is an integer. What will be the value of n? The value of n can take any number excluding 0, because if it is 0 then equals to 0, that means it will not be validate. So this integer n, it is also known as the quantum number, which we will discuss later on. It can take value 1, 2, 3, 4, and this gives the energy of particle in one dimensional box. And what is this energy? These energies are not continuous energy. These energies are all discrete energy. Now what is the meaning of discrete energy? Let's say you are moving in a stair like this, so your energy is actually increasing continuously. But if you move in a staircase like this, then you are getting from this to this, so your energy is actually increasing discretely. In between there is no energy, right? So your potential energy is increasing discretely. This is an analogy. We will discuss more on energy quantization, but let me just tell that E equals to 0 is not possible, because if E equals to 0 inside the box, then psi also 0. It is not y, this is psi also 0, which means that particle do not exist, which is not true. So E can take all the values except n equals to 0. So what are the values he can take? He can take n equals to 1, so h square by 8 m square. It can take 2, 4h square by 8 m square. It can take n equals to 3, that is 9h square by 8 m square, and so on. So this is nothing but your energy quantization. Now how to explain it for the electrons? Let me explain it in a more easier way. So let's say that one electron is there in n equals to 1. Let's say one electron is there in n equals to 1. Now we are promoting this electron from n equals to 1 to n equals to 2. So what will happen? What will happen to its energy? Let's say it is n equals to 2. And then again we are promoting this electron to n equals to 3. So what will happen this electron energy? So if n equals to 1, that means if electron is present at the lowest energy level while n equals to 1, then its energy is h square by 8 m square. If it is present in n equals to 2, then it's nothing but 4h square by 8 m square. And if it present in n equals to 3, then it is 9h square by 8 m square. This is nothing but the energy quantization. So electron is moving from 1 to 2, it can go from 2 to 3. In between no energy is possible. In between 1 and 2 no energy is possible. Only h square by 8 m square, 4h square by 8 m square, 9h square by 8 m square, and so on. These energies are possible. So this is nothing but your quantization of energy of the electrons. Based on this principle of energy quantization, the whole electronic industry is actually depends on. Not only electronics industry, the other field which utilizes the concept of this energy quantization of the electrons also depend on. So now what is the use of quantized energy? We are talking for the last 10 minutes about energy quantization. What is the use of it? Lots of uses are there. Fluorescence, it is nothing but emission of energy when electron come from higher energy state to lower energy state. We will discuss later on. Then microscope, the whole all microscopes actually utilizes this energy quantization of the electrons. MRI imaging, one of the most important medical instrument for various diagnosis of the disease, where energy quantization is used, and many more. Lots of applications are there of energy quantization. So today we have addressed the particle in a 1D box model. We have solved the Schrodinger wave equation for one dimension, and we have also understand how the electronic energy is quantized. In the next video, I am going to explain the quantum confinement. See you soon. Thank you.